participants and our esteemed speaker, Mr. Paul Meenan. Without wasting the time, we would like to invite Mr. Paul Meenan. Mr. Paul, you are welcome. Please start your session.
So today is going to be an intense day of as much information that we can give your way, and hopefully the engineers watching will be able to watch back on the YouTube and break it down, analyze what we're saying, go away and validate for yourself, go away on your own research journeys, so that you can greater understand this huge topic of earthing and bonding. So I shall go forth. So yes, we're going to look at some of the hidden mysteries, because I found in researching this, earthing isn't just sticking an electrode in the ground and putting a green and yellow wire to it. It's far more complex, and the word configuration I will use consistently through this webinar. But I'm going to kind of have lots of different things in this webinar. I'm going to introduce a brief timeline. I'm going to look at some of the early references, which I find fascinating, and hopefully you will. I always had the view, you don't know where you're going if you don't know where you've come from. So for me, fundamental principles understanding the history, it's very important for a competent engineer to understand the journey of technology and safety. I'll introduce you to the standards, because nobody really taught me how many there were. So I'm going to take you on a whistle-stop journey through all of the locations of research and additional knowledge. I won't be going through any of them in detail. This is about informing you so that you can get the best position to make an informed judgment when you're selecting and erecting or designing your electrical installations. I'll do some what we call in England some Janet and John, some first principles, so terminology from our UK regs. I will also introduce you to our UK regs. We'll look at some pictures of some good and bad. I'll also talk about how our networks in the UK have some risks, and maybe that could apply to the networks in India. And I'm sure Krish will jump in and say, yes, Paul, or no, Paul, and put me on the right course. I'll talk about your impedances and resistances, because that's some fundamental parts of understanding earthing as a system. And we'll touch a little bit on just bookending Krish's last excellent RCD webinar that he did some months ago. So let's get straight into this. Let's start on a brief timeline. And what we will do is we will look back 277 years ago was one of the earliest references I can find to a term called telluric currents. In modern terminology, telluric currents is earth currents. So 1746, that's the earliest I found. I'm sure somebody watching will probably go, oh, no, I've got something going back even further. Well, that's one of the first documented pieces of discussion on earthing of electrical systems. Now, fast forward, these are key dates in the UK, and just on that journey of earthing and bonding. In 1871, that cheeky chap with the cap, he formed the Society of Telegraph Engineers, which we commonly now known as the Institute of Engineering and Technology. We fast forward a little bit more, 1872, Sir Charles William Siemens. All of us watching will know Siemens products, Siemens technology, major global infrastructure provider, protection devices and all sorts of electrical systems. He was elected the first president of the Society of Telegraph Engineers. Interestingly enough, one of the first propositions in 1880 was to rename the Society of Telegraph Engineers to the Society of Telegraph Engineers and Electricians. Evidently, the Society of Telegraph Engineers didn't have enough funds, so they thought they'd bring the electricians in as well. And there's the actual extract from the journals. Now, everything I'm doing in this, I have research from journals, but I'm also giving you my view and opinion. Please feel free to form your own opinion and go and research this for yourself so that you can find out your own hidden mysteries of our wonderful electrical industry. So one little hidden mystery that I found was this gem. Now, in our early records, it's actually in one of the journals. It says, no doubt if the society was being started, the proper title would be the Electrical Society. I absolutely love that. I wish they would have just called it the Electrical Society. It's a great phrase. But unfortunately, it wasn't, because that institute was on that journey already. So a little hidden mystery for you there. So going back to 1881, Sir Charles William Siemens, he introduced one of the first public electrical distributions in the UK in a place called Godalming in Surrey, as you can see from the map of the UK. and there's an actual image of it. That's not the actual bulb. And he introduced a number of street lighting. Didn't go very well. Cables were laid in trenches, they were laid in gutters, and there was lots of accidents and injuries. So it was that first public trial. It was actually a disaster. So they went back to gas lanterns, because this was the first electrical from gas lanterns. Gas lanterns had been in the UK since the early 1800s. So, little interesting fact. And then 1 year later, the first edition of the wiring regulator was published. So 141 years ago, the first edition, or first wiring rules. And we'll capture a few little nuggets from that in a bit. If we fast forward 5 years to 1887, they renamed the Society of Telegraph Engineers and Electricians to the Institute of Electrical Engineers. And so it stood for many, many years. So the IEE, a very famous term. But just keeping to the subject matter, 1939 is the earliest reference I can find to an earth-related protective device. So many years ago, we used voltage-operated earth leakage devices, and this had a lot of information on geotechnical impedance, resistance of soils, and really went into the subject matter of how do we look at the resistance and the quality of the ground that we're connecting our fixed installations to. Fast forward to 1992, the British Standards Institute, or the BSI, they effectively jointly published the wiring regulations with the IEE, and it became a British standard, BS 7671. In 2006, sometime later, the Institute of Incorporated Engineers and the Institute of Electrical Engineers merged to create the IET, and that's what we have now, the Institute of Engineering and Technology. So it's been on some journey now for a number of years. So that's kind of some key points I just wanted to throw out there, just to show the journey that we in the UK have been on, and there's also always a cascade around America and South Africa, and that knowledge doesn't stay in England, it's dissipated around the world. So if we look at some of the early references to earthing and bonding, and this is what I find fascinating. Many years ago, there was journals published. So they would go to their wiring regulations committee, like Mr. Kumar would go to, and Krish, and they would debate stuff. But in the old days, everything was recorded. So the debates and the opinions were recorded. And these are all published and they're all publicly available. And that is where most of the history of early electrical engineering is fascinatingly debate. And just here on the screen, February the 10th, in 1881, there was a paper written on earth currents. And I have found on this journey an amazing, mind-blowing journey that people went on earth currents. So there was talk in these papers of magnetic lunar effects on the earth, generating these telluric currents, and people went off experimenting with plates in the ground all around the globe to measure and find energy. And they believed that the movement of the oceans was affected by the moon, and obviously all this good journey of knowledge we've had from physicians and geotechnical engineers to understand and try and debate what earth currents are and if they're good. Again, there was that feeling that the energy was coming from the ground because of the moon. So lots and lots of fascinating debates. I could do an entire webinar just on that. One of the wonderful things on these papers, everything's published, is the responses from the peers. And the peers, this is a great point, where one of the gentlemen in the IEE said, Mr. Adams has said our knowledge of the subject is very meagre. How true, but how fascinating as well. But he has discussed the evidence, and that's what good engineering is about. It's discussing what evidence you have, inserting it with your opinion, understanding your duties to protect people and property. It's great being an engineer. Just going back to 1882 when the first wiring regs, this is an interesting bit on earthing. So this is one of the first standards that referenced earth, and I've just put the paragraph on the screen there, and it states, it cannot be too strongly urged that among the chief enemies to be guarded against are the presence of moisture, as it is today, and the use of earth as a part of a circuit. Moisture leads to loss of current and destruction of the conductor by electrolytic corrosion, and the injudicious use of earth as part of the circuit leads to magnify every other source of difficulty and danger, which is fascinating when you consider, there could be danger if you don't have a good earth. You could have a rise in voltage. You may not have your protective devices protect you. And in 1882, they went from, in 1881, talking about how good earthing is and telluric currents to, maybe it's not so good. So there's been a huge journey of learning there. Now, moving on to atmospheric electricity, what we lovingly call now lightning protection. So I have done quite a bit of reading in the journals, and on the 27th of November 1872, with Mr. Siemens in the chair, there was a paper read on lightning and lightning conductors by a member. And the narrative on the left is fascinating. In this country, not only have trees been shattered, cattle destroyed, public buildings struck, and private houses injured, but human beings have been killed in such numbers that if tabulated, they would probably cast into the shade the massacre committed by even our railway trains. Oh, that's what an interesting analogy there, the massacre of railway trains. The average number of deaths due to lightning in England previously to this year was 18, France 95. So you can see in the 18th century, there was a huge gathering of data and trying to understand things. Mr. Simmons, the well-known meteorologist for many years, devoted his attention to the subject, mentions that in 2 storms in June, nearly 200 separate accidents came under his own knowledge, including the death of 10 persons and injury to 33. Upwards of 60 houses were struck, 10 or 15 were burnt down, 23 horses and cattle, and 99 sheep were killed. And it's kind of saying, well, that was 2 months. What for the whole year? It also talks about telegraphic systems and railways, and lightning strikes do cause huge atmospheric transients, which we know now in modern worlds. We do put surge protection in England. A lot of places we assess the risk of lightning. Interestingly, there's some, the Escurial, since its completion in 1584 in Spain, has been on fire no less than 7 times. 1587, 1590, and it goes through to 1872. The causes are unknown, but at least 4 of the fires arose from lightning. But not one lightning rod was introduced to this building. So there's some fascinating history, and you can see that people have gone on a journey of understanding their knowledge. This, to me, is the earliest reference I can find to a lightning protection system. So it's from the same paper, and it says, I've recently had the pleasure of inspecting a plan adopted by Mr. Hyatt of Painswick House near Stroud, Gloucestershire, by which he has succeeded in converting a 2-inch wrought iron pipe used for ventilation of drains. So in England, we have cast iron drains that go above where the windows are to cross up just above the roof, and that allows any smells from the drainage system to vent to atmosphere. So the wrought iron pipe is carried from beneath the ground 8 feet above the top of the highest chimney. It is therefore surmounted with a vane having a sharp point some inches above its centre. The vane and the point being of copper. It is also connected with the lead coating of the roof. It appears to me an excellent admirable system worthy of greater adoption. So this chap found in this house that lightning strikes were hitting that, not destroying the building, not causing fire. Henceforth, this was one of the earliest debates I can find that created what we now know to be the external straps or rods that go down the outside of buildings to protect the building. So that's kind of just some early history there. I'm going to take you into the standards now. This will be the whistle stop bit. So obviously we all are familiar with IS 732. I am on a journey of competence development. I am finding these standards fascinating to read because obviously local conditions will apply around the world. But they are written in the same spirit of the IEC 60634 or BSEN 60364. And we'll get on to what they all mean. Obviously, the latest document that Mr. Kumar and Krish and his teams are doing, they're looking at SP30, recent publication known as the National Electrical Code of India. It's an interesting document. I've been reading it. It's kind of the equivalent, I suppose, to our guidance notes that we have. That's kind of where I've looked and read it, but it's got some very good guidance in it as well, some interesting engineering thought. Now to introduce you to England. So we have the wiring rules, which has now become the British standard. They have different colour covers every time they're reissued, and it's known as British Standard BS 7671, issued 2018 and then amended twice so far. The last one is 2022. We are due another one in 2 years, I believe. Yeah, 2025. So they're amended every 3 years. And then once they've gone through 3 amendments, it's a full revision of the standard. So yeah, it's we never stop. And for those who obviously work in our industry, we are never stopping learning. We're always improving the standards. One of the key things I always say to people in England is, for the electricians, the engineers, feedback to the committees. Give them your opinion. Does this work? Does this not? It's so important. So that's based up of exact same IEC 60364. They go through the requirements of those series of standards and they integrate it into one document. And this is the structure of it. It has 8 parts. 8th was the more recent introduction. So it has a standard introduction with what I love to call the fundamental principles, chapter 13. If you're interested in reading it, if you read those 6 pages, you'll become very au fait with the standard. It has obviously the definitions, the assessment of characteristics, which any good engineer should be doing. How do we protect for safety? How do we select and erect? How do we inspect and test? And also look at the more subtle special locations where there's more inherent risks or specific protection measures we need to take. Cattle, medical, fairgrounds, electric vehicles. And then chapter 8 is a new chapter, functional requirements, and that comes from the IEC 60364-8-2. So the numbering system is in line with the IECs. And that basically covers energy efficiency, prosumerism, all the adoption of modern battery storage and all that good stuff. So, and that's growing. That part is growing. So just to reiterate, the wiring regulations is a joint publication from the IET and BSI. So they all sit on a committee together with various industry bodies, manufacturers and peers. But taking a stop and step back, how does all this create the wiring regulations? Well, the IEC, International Technical Committee, they have a Committee 64 and they publish IEC 60364. That then goes to CENELEC, which is the European Committee for Electrotechnical Standardization. They also have a Technical Committee 64, and they obviously produce the harmonized documents, the BSEN 60364s, all the way down to the Committee JPEL, Joint Power and Electrical 64, and they produce the IET document BS 7671, 18th edition. So that's kind of the journey they go on. So if you want to know what's coming, you might want to expand the way you look at standards. So if you literally want to predict what's going in the world, there is a way of doing it. And you just got to look up and see what the changes are there. Now, CENELEC is made of lots of European countries, obviously. Some non-European countries are actually CENELEC harmonized. So that's one of the positives of the EU, that everybody's trying to work to a common standards framework. And more importantly, standards, I'm sure Gopa has said this, standards are a minimum criteria. Standards are not something you look up to and you argue with. They're a minimum criteria for you to make an engineering assessment and a judgment, and you shouldn't be able to depart from those standards if you still have the same degree of safety and performance, because that's what competent engineers will do. Just to kind of put into context the journey we've been on in the UK, first edition published 1882, it had 4 parts, 3 to 4 pages. Now it's 8 parts and 608. And I'm sure when your regulations are updated, they will grow. Technology is growing, AI, all the new technologies that are coming. We need to be informed. So yeah, standards grow, and that's not a bad thing. And a lot of people don't like it, but if you adopt the principle of, yeah, fine, then it's easier to absorb that knowledge. So getting onto the earthing standards now, huge journey. As I said, 1939 was the first protective device that relied on earthing and talked about earthing, but the actual earthing standards themselves in 1965, CP 1013 was published by the Council for Codes of Practice, or the British Standards Institution. That was then updated and renumbered to BS 7430, which is anyone in Europe, you mentioned BS 7430, they'll know what you're talking about. Well, the first edition of that after 1965 one was 1991. And then in 98, it was completely rewritten. 2011, again, updated into the modern format, and we're currently working off Amendment 1 of 2015. So that's where we go to for a lot of our fundamental nitty-gritty earthing and bonding details. So a lot of the HV engineers, a lot of the lightning protection engineers, a lot of the earthing specialists, this is their book. This is what they use a lot of. But as good engineers, we shouldn't just limit ourselves to one standard. That we will make mistakes. We need to consider the guidance in other very well-educated publications from experts. So you look at BSEN 50310, which is telecoms bonding for buildings. You know, if you have data centers, a very important standard. We have guidance in chapter 54 of BSM 671, which relates to the IEC standards. We have guidance notes specifically just on earthing and bonding. If we carry on, if you want to look even further and look up, there's an IEC standard, International Electrotechnical Vocabulary, and it just harmonizes and standardizes all the terminology. Now, we're not quite there yet, to be honest with you, because different standards do still use different interpretations of stuff. But as I said, if you want to know the journey you're on, why don't you look around you? So in Australia, they have their own wiring rules. Ireland, the 2020 IS 10101, excellent standard, really good. They're slightly ahead of where we are in the UK. And in my opinion, the most advanced standard out there is actually the NEC 70. Yeah, so it's NFPA 70, National Electrical Code of America. That's constantly being updated. So and that will filter in around the globe, and people, the experts like Mr. Kumar, will take the best parts and the lessons learned and the assessments of technology, and they will implement them into their next editions and discuss. And coming back home, we had 7430, but in India we have IS, Indian Standard 3034. Which I have been reliably informed by Krish is our equivalent in India of 7430. And then obviously with that, you would most certainly want to take advice from Indian Standard 732, which are the Indian wiring regulations, and then SP30, your guidance and your National Electrical Code. So all of them will contain some fundamental knowledge to make an informed judgment. Moving on, if you're a HV expert, lots of people are, BSEN 50522, which is earthing of power above 1 kV, and then BSEN 50122, which for me, who works in railways, very important document. There's a whole suite of these. I could go on for hours, could do a whole webinar just on standards. This covers the electrical safety earthing and the return circuit of railway traction systems. It's a fascinating one, especially the interfaces to LV. So that's for the HV guys. If you wanted to look further afield, the IEEE Standard 80 in America and parts of America, which is a guide for safety in substations. Grounding. Grounding is very similar to earthing. The IEEE guide for measuring earth resistivity. These are some very good standards. Standard 81 from the IEEE. If you want to further research the subject, if you're writing your own papers about the effects of energy dissipation and good earthing or bad earthing. Now in England, just coming back on the HV side, we have something called atmospheric transients, lightning protection, and we have 4 BSEN standards, 62305, part 1, your general fundamental principles, your part 2, your risk management, 3, the physical damage to structures and life hazards, and then 4, the electrical and electronic systems within the structures. Now in England, we do a risk assessment. We use the guidance, as you can see on the screen, we use flash density maps, where the weather services record all the lightning strikes so that we can ascertain the level of risk so that we can design a proportionate lightning protection system. So lightning protection systems are risk-based. So if you have a risk assessment, then you will design from the risk assessment. If you don't have a risk assessment, then in England, you'll be told to go away and look at 62305. It does need an update, in my opinion, and it probably needs an additional one as well for testing. So it could be a part 5. Just again, my opinion, be great to see a standard on testing of lightning protection so that we can harmonize that a little bit better. Again, further afield, lightning protection, NFPA published 780 again this year, the standard for installation of lightning protection. And there's also some secondary research documents from API 545 from the Energy Institute on verification of lightning protection in specialist areas. So there's lots and lots and lots of standards. And that was just a summary of some of the standards. I could have gone into 10 times the length and detail, but it's good to know the first part of a journey of making an engineering decision is understanding what you know, understanding what you don't know. When you don't know, where do I go and get that knowledge? And the best place is standards. So I always say to people, if you can read and you know where the standards are and you can access them, you're on a very good journey of developing your engineering knowledge. But let's take it back a bit. So let me introduce you to some of the first principles, the terminology. So in the wiring regulations, I see somebody has got their hand up, but if it's okay, I will answer questions at the end. Apologies, I should have said that at the start. Unless Gopa wants to chip in.
Yeah, we will take care later.
Okay, great. So in BS 7671, we'll put your questions in the chat as well. I should have said that, so apologies. 7671 has Earth defined as the conductive mass of Earth, whose electric potential at any point is conventionally taken as zero. Now, potential is a word that we love to use in standards. What does potential mean? Voltage. So the voltage is conventionally taken at zero. So, oh, hang on, this works. Earthing is the connection of exposed conductive parts of an installation to the main earthing terminal of that installation. Okay, and that's a picture of an earth bar that I installed actually on a job where we bonded the steelwork and we had an earthing conductor and CPC. It was a heavy industrial job, as you could tell. Probably should have put that box in an enclosure to protect it from external influences. So we don't always get it right. Just to show you some simple pictures, this is how I learn. I'm a visual learner. There's a chap there standing in a building. The earth electrical appliance, generally of a kettle. If you're going to have a kettle that's metal and it becomes live or energized, what you'll have is somehow a breakdown into proprietary insulation within the device or of the cable. That then allows a line conductor to come into contact with exposed conductive metalwork. And in theory, when that does, the energy will dissipate down the circuit protective conductor in a manner sufficient to allow the protective device to trip down to the general mass of Earth and off safely. So low impedance is very important for safety. Now, what happens if you don't earth the appliance? So maybe the same kettle, but there's no earth connection. And I know in India, you guys have different practices. So let me just get onto this and we'll maybe talk about it. So electrical appliances that have not been earthed, as you can see, you provide that fault path. So you will effectively receive either an electric shock, which will cause you harm, or you will be electrocuted and dead. So there's no in between really there, to be honest with you. It's either you get very lucky or you get dead. So earthing is incredibly important because it will take that least path of resistance through you down to the ground, and you then have to hope you've selected your devices accordingly, which we'll come on to. Now, I adopt simple rules to learn this stuff, and I like the rule of three. So what is an exposed conductive part? Well, in the wiring regulation, there is a paragraph, but if you break stuff down, so if you're an apprentice or a learner and you're learning this, get a highlighter pen. Highlight things, break the sentences and the paragraphs up so that you can break it down into simple stuff. So exposed conductive part is a conductive part of equipment which can be touched. Okay, but it's not normally live. Fine, but it can become live under fault conditions. 3 parts to that. Very simple rule to remember exposed conductive part. Yeah, so it's a part of equipment which can be touched. It's not live and it can become live under fault conditions. But then if we look at extraneous conductive parts, and I spent when I was younger a lot of time trying to work out what the difference between the two is. Again, use the rule of 3, break it up, highlight it. Extraneous conductive part is a conductive part liable to introduce a potential, a voltage. It's generally at earth potential, so in theory a pipe that comes out of the ground should be at 0 volts and not forming part of the electrical installation. So if you have an oil pipe, a gas pipe, a water pipe that comes in from the ground, we assume that it is at 0 volts, so it's extraneous. But what do we do then to ensure safety, that it doesn't become part of a path? So what we do is we do equipotential bonding. And equipotential bonding, or equal voltage, is the electrical connection maintaining various exposed conductive parts and extraneous conductive parts at substantially the same potential. So we keep using the word potential, and it's my personal opinion it should be deleted and just use the term voltage. So if you look here, you have an installation, an electrical appliance that's become live due to a fault, and that person there could be touching a water pipe, which is brought in from the outside. Now, the kettle is an exposed conductive part. It's exposed metalwork, forms part of the installation, generally expected not to be live, but could become live. And the extraneous conductive part is very similar, but it's generally considered 0, and it could become live. It also could help form a path. As you can see, the path of fault could go through the gentleman who is undergoing that fault condition. Now, simply put, equipotential equal voltage. So if I bond that water pipe as it enters my building, in theory, I should have a equal voltage. So any fault currents that, or voltages that connect to any earthed equipment should rise and fall at the same time. And what I'm going to do is I'm going to just narrate a little video here. So a massive thank you to the chaps at Grey Matters Academy, wonderful online training provider. They are industry leading in HV, earthing design, earthing services. They're brilliant. And they've gone to a lot of time and consideration to create this video. So I'm just going to press play and narrate it. So what we do is we have energy coming off the grid, high voltages. It's transformed down, goes into overhead poles. As a substation, typical substation, it could be anywhere in the world. And what we have here is a HV wire that dewires, and we have an earth potential rise. And as that grounds itself or earths itself, it dissipates energy. Not only do the houses lose their power supply, which nobody wants, but often happens in a lot of HV installations where there are faults, but the earth potential continues to dissipate through the ground. And this is where earthing and bonding is really important, because critical systems like data centers, that energy is dissipating through the ground and could appear on earthing systems, could cause damage. It could cause damage to cables that are nearby. It could cause step or touch potentials, as you can see. As that gradient dissipates and the voltage lowers the further it goes, it can energize and appear on exposed or extraneous metalwork and circuits. And electricity has a tendency to go where it wants and do what it wants. We have a requirement to control and manage and configure that electrical installation as best as we can. So how do we do it? Well, we basically bond everything together with a bit of green and yellow cable. So that is a cross-section of an installation where you have the incoming supply cable, the main switch, you have a copper earth bar, and we bond gas, water, other services, ductwork, and sometimes, depending on the earthing, we put electrodes in. There is a requirement or a recommendation now for new installations to have electrodes. That wasn't necessarily the case in the UK. So that's kind of just some fundamentals there on the terminology. I'm going to show you some good and bad examples. That's a terrible one. Obviously a wind-up. I'm sure lots of people have seen this on social media. That's not earthing. That's called taking the mickey in England. But it's quite humorous to see that we can have some warped sense of humours. That is a main earth terminal, as you can see, label that says safety electrical connection, do not remove. That's an industrial cooling the tube one, actually, on London Underground, and everything is labelled, heat shrunk, connected to its own terminal, and you have a drop link connection so that you can disconnect and separate the earthing so that you can test safely. So that's a good practice one. This, not so good. Yep, 10 points for the electrode, maybe not into the bucket of dirt. Not great practice there. This is a picture of a supply, which is actually in India, and it shows the earthing coming off the sheath, very similar to England. And in England, we have old networks. You think our networks are near 100 years old. So we have metal cutouts, pitch resin filled, which can leak when they get hot because of loading. And that's just an image of an earthing system that connects to the sheath of the cable. It's an old lead, bitumen impregnated sheath cable. These are more modern in England. We have a supply cable comes into a service fuse, and a lot of places the earthing will connect either to the sheath of the cable or actually connect to the neutral, and their TNS, TNCS systems. One of the other things that you get on earthing is you can get some hazards. So that's a 25mm conductor that had 198 amps flowing through it. So when it goes wrong, it can go wrong terribly, which is why configuration of your earthing is key. It's very important. If you have access to clamp meters, earth leakage meters, I always recommend, and so do the IET, that we look at, before we work on earthing systems, we put a clamp to see if there's any energy or any charge. There's 134 amps on that one, not great. And sometimes the effects of having current flowing through the earthing can be quite disastrous. On the right, there's a gas meter that's melted through a fire caused by the sheer level of energy that was pumped through it, and also insulated pipe work where the insulation got so hot it melted and fell off. And that's on pipes you don't expect to be carrying electricity. So in England, we don't get it right, and there is a reason behind that. is a picture that I took. There's 20 amps on an earthing conductor. So that's the fixed electrical installation to the power supply. Don't really want 20 amps on an earthing system, considering that in England, I was taught that it's a benign conductor with 0 volts. Generally, there are millivolts behind this, but we'll get into that phenomenon in a second. One of the scarier images of my collection is where you have the service cutout, which is the grey thing at the top. You have the fuses on the floor, but you still have energy. So I've isolated the installation, or as we call in England, the disconnection and separation of all sources of electrical energy in such a manner that it's secure and there's still power flowing. So there's a problem on the earthing. So what can we do? How do we understand that better? Some good practices here in England. When we're building stuff, we use earth tapes, welded connections, and we create pits to create a large earth mat. They can also use rods as well. That gets covered up. We can also connect to rebar. So piling, that's a crossrail transformer there. And what we did was we basically put 28-meter piles in the ground, 150 of them, and connected the earthing conductor to the pile cap. And we got a fantastically robust, low impedance earth. So you can use structures and you can use metalwork in the ground. You just make sure that you protect it from corrosion and you inspect it accordingly. One of the other, my favorite things that I've recently been doing over the last few years is getting rid of rods, because they can be inherently dangerous, banging a rod into the ground and hitting a buried surface, especially in England where the roads and the streets are quite congested. So I've been trialing some discs, which are carbon coated disc with a copper connection from a company called Earthing Services. They're used in America at the bottom of telecoms poles to give a local earth reference, so similar to a rod, but a lot safer. It just bolts onto the bottom of the pole. Now, this is where I take the mickey out myself, because occasionally I do like to do some work, and there's me digging a hole, not very deep, because you don't need to put them very deep, putting in some conductive concrete. I know in India, I believe we use different recipes for earthing of systems. I've seen sugar and salt and all sorts of things, but we use a conductive concrete. You don't have to, by the way. You can just drop that in, as I did there in the image. And what we were doing is we were replacing a very good friend of mine's earth electrode, which had rotted and corroded. So we put 2 discs in, dug a small trench, bare cable, and we got some fresh soil, covered it up. We got 6.8 ohms, which is very good considering, you know, your recommended 21, 200 ohms. So that's pretty stable, pretty good. And that was a job I did recently in the last year or so. So getting back to those images where we had that earth current, what could be wrong? What hidden mystery have we found now? The hidden mysteries we've got is the network risks, or what we call in England the DNO, distribution network operator, or the distribution system operator. I believe in India they're called the discoms or supplier. Again, feel free at the end to kick me if I am incorrect. And one of the things that got raised to me was this health and safety report. So in England, we have health and safety alerts if there is an incident. And this is an incident from a natural gas supply to a house where a coat, as you can see, fell upon the gas meter, which had something called neutral current diversion. And that neutral current diversion was of sufficient level that it actually burnt the jacket. Now, this is a pipe that is benign, that shouldn't really have this, but it did. So what's going on there? Well, in England, we've got lots of different electricity networks. Many years ago, when they first started, we had dynamos or generators in the houses, and it was generally for the rich of society to have electricity in the home. And then around the 30s, the national grid came in and we created networks, regional electricity companies. They're now called DNOs. And that's how England is divided with all the different private companies. I live in the area for UK Power Networks, just down by the right-hand side of London. Now, these networks over time will, like any electrical equipment, they will age. They will suffer impact. They will suffer corrosion. Like anything, if they're not looked after or maintained, or they will naturally just reach the end of their life cycle. Now, if you think about that, in the 1970s, the cabling in the streets was 50 years old, so they introduced new cabling, new earthing systems, and we now have a hybrid of the new and old. But before we get into that, there's an IET article, just Google broken pen, very good article from Michael Peace. who discusses the subject very succinctly. And that is the hazard. That is the hidden mystery that we're now on a journey. So everybody in the UK is on a journey looking at broken pens, protective earth neutral conductors, the hazards related to it. And what we'll do is we'll go into that now. So I like to do pictures. So this is a very basic picture of a substation with an earth reference. And in England, what we have is basically a combined neutral and earth in the street now. Because of the age of the networks, that's what they've done. We have a live conductor that goes out, a line conductor, sorry, goes into the house, into a cutout, and then you have an earth terminal where the water and gas will be bonded, or any extraneous services. Excuse me. So that's normal. That's how we wire things, and obviously energy goes in, goes out, back to the transformer, no problem at all. That's how it should work. And then after 50 years, 70 years, these cables will get old, they'll be jointed, the joints may not be good, and like with any loose connection, loose wires start fires. Now over time, your impedances or your resistance of your cable can go high, and what will happen is that neutral, say from house 3, the return current, when it tries to go back to the substation, it will meet a high resistance, so it won't want to go there. And this leads to then a network imbalance, because what's going out is not coming back. So what we do is we then find that when you put a clamp meter on your earth wire, that water, which is a lead pipe or an old copper pipe in the ground, some of the energy will divert into those lead and copper pipes, and they may travel all the way through and divert around the high resistance joint and into house number 2. So number 3 can be fed via the gas or water main into number 2. So that's known as diverted neutral current or neutral current diversion. And eventually, I've always said that when you've got energy that shouldn't be there on your earthing system, that's a precursor to a failed neutral in the supply network. So it's one of the things that we look out for, and we call it a broken pen. And the reason why is I'll show you in a second. Now, what that leads to is if we do have a broken pen, you could get potentially 230 volts in house 3 with step or touch potential. So you could go outside, touch your tap and have 230 volts. Further down the line, if you have a broken pen where you've got multiple houses across phases, you could have 400 volts, which could lead to great injury. And also, if you get 400 volts, you could find your televisions and all your electronics blowing up or failing. So that's as simple as it gets. On a single house, much easier in the countryside. Combined neutral earth, if you fail on the connection, then your neutral earth return has only one way to go, and that's straight down to ground. Hence, we're recommending local electrodes now as well. So that's known as exported diverted neutral current. Just to give you some statistics, is this a problem in the UK? Yes, it is. It's not a huge problem. It can be managed, but it's one we're trying to raise awareness of. Last year, according to a Freedom of Information request, we had 474 broken neutrals on supplies, which isn't a lot in the scheme of things, but is enough to be wary that as the networks age, the hazards increase. I haven't got 2022's numbers yet. Just worth noting, on Indian standard 732, page 38, it actually mentions diverted neutral current 3 times. So it's quite interesting where protective earth or pen conductors should be earth where they enter any buildings or premises taken into account. So configuration is key. You may want to think, well, what do I bond? Where do I bond? How do I earth it? Do I introduce a greater level of diverted currents? Especially if you have a failed neutral on the supply, the more earthing you have, the safer you may be, but you may actually be masking the failure of the neutral because all the network neutral will come into your property, henceforth the images. Now, just to show you what it's like in England. So this is actually a picture, one of my favorites. It was taken by me, and the cable on the right is a lead sheathed cable. So this was installed in the 30s. And what you have is effectively 3 phases, L1, L2, L3, and a neutral. And the lead sheath is a wonderful low impedance earth conductor. The one on the left is the modern cable installed in the 70s, which had a 40-year design life. And that's called a concentric. So what they did was they went with 3 phases aluminium, and they then went with a copper armoring or sheath, and that's the neutral and earth combined. Henceforth, in that photo, they split from the neutral and earth. Now, the problem with that is with the combined neutral and earth, if you lose it, then you potentially have diverted neutrals, you potentially have a rise in voltage. So This is a challenge at the moment in the UK. It's a growing challenge. It's nothing that people need to panic about, but we just need to raise the profile so that people can check and ensure they're safe. Safe working is key. Here's some more images to show you how dangerous this can be. Just some clamp meters around earthing conductors, 43 amps, 58 amps. So it is very much real. It is also a real thing on railways. Traction return can enter stations, and that can cause chaos with the station communications, interfere with EMC issues. So, and these are real things that happen nowadays. So we're still on a journey of evolving learning. Just on that, obviously, step and touch potential, we covered it in the video, but just some visuals. In Ireland, we have a lot of problems with dewirements, where they kill our beloved cattle. That's an incident in Ireland from an overhead pole that dewired. Cattle obviously can't take step voltages. So it's something to be mindful of when you're designing an earthing system. Have you considered your touch potentials? Have you considered your step potential, especially on high voltage systems? And there's some good videos online that will help explain that visually further. On railways, we have some nice simple visuals on touch and step potential. We use PPE, we have insulated boots, we have rubber matting in switch room, all sorts of stuff to protect us. This is my favorite picture. It was taken at a domestic property, and that just kind of shows you a broken neutral on the supply, 158 volts, and the clip is attached to the outside water tap, which people plug their hose in. And then the electrician just put put a drill into the ground and measured 158 volts. So that just proves the concept of, voltages, they grade across the ground. They can be a hazard because I could touch that drill bit and also the tap and get an electric shock. So just be careful when you are configuring your earthing and bonding. Now, one of the key things for earthing and bonding to its success is ZS, ZE, and ME is the phrase I use. In electrical installations, again, if there's any learners on there, I break it into three concise parts: resistance, impedance, ZS and ZE. Resistance, we look at the resistance when we're looking at earthing of the soil, of the cables, of the exposed parts, of the extraneous parts to prove safety. Once we have those resistances checked and we energize our systems, we then look at impedance. Impedance being the sum total of resistances at a point. It's a fixed point. So you go to a socket, a light, a fuse box, and it does a test. It checks resistance of all paths of resistance. And we want nice low impedances, because if we have low impedance, we then have lots of energy flowing to activate our protective devices. And we ensure that the protective devices work. Now, the difference between ZE and ZS, very simple. ZS is a resistance reading taken at a point, and the ZE is the external, so our connection to the general mass of Earth. If we do not have a good ZE, which is noted on your certificates in SP30, you don't have a guarantee of safety. So that's worth noting. Now, the reason I raise this is because we have external impedances of all electrical installations when we connect the installation to the general mass of Earth. And in the UK, we are getting reports of higher ZE readings. Now, the Energy Networks Association, who are the voice of the electricity networks, they issue guidance. So I don't know if Indian suppliers issue guidance in a similar manner. I'm sure we can talk about that in a minute. And are higher ZE readings the future? Well, naturally, with age, if we're not maintaining stuff, then yes. So how do we kind of mitigate that? Well, you saw in the photos I was putting in discs or rods. There's some really good guidance out there as well, where it kind of gives you, in England, we have a 100 amp service head, and it gives you the earth fault loop impedance, and it tells you that, 90% will have below 0.34, but they also acknowledge there will be installations, millions of services where they may be higher than that. So, and it's good that they're publishing this sort of stuff, because obviously we need these ZEs to make sure we've got sufficient fault current to flow. One of the more scary points in the UK is note 2. Distribution network operators are under no obligation to design or maintain networks to provide a particular maximum value of earth loop impedance. However, under our electrical safety quality continuity regulations, they are obliged to maintain the earthing. So a little bit of contradiction there, and it makes it very grey. Always an interesting debate with your network supplier, for sure. But some Companies will publish very simple guides to earth loop impedance, maximum values, 0.35s, depending on the level of energy, 0.8. There's standard values for the different earthing systems. We have what we call PME, protective multiple earth, also known as TNCS, and a separate neutral and earth, also known as TNS. And the networks originally were TNS. They're now pretty much all combined neutral and earth, unless they're on a private transformer. Personally, I think separate neutral and earth was always the way to go. But just to let you know, some DNO companies will allow a hybrid. So the photo you'll see in a minute is a hybrid of multiple earthing systems. It can be confusing for an electrician when they're trying to ascertain what it is. I've always said go for the worst case. So in exceptional circumstances, hybrid earthing, and that's from Northern Ireland. In England, it's the norm. There are lots and lots of guidance in England for voltage fluctuations, application of PME, connection of generators, all sorts of stuff. Now, this is three of the more common systems we have. We have TT, Terra, which is earth electrodes, if you only have a supply live and neutral. We have TNS, Terra neutral, separate, so it comes in completely separate. And then TNCS, Terra neutral combined separate, which is that cable there. It comes in from the bottom and basically connects into the fuse. But as you can see, that's a hybrid arrangement. In fact, if you look at the white cable from in the earth terminal, that could go to an earth rod. So is it TT, TNS, or TNCS? More than likely, it's a TNCS that somebody has tried to lower the impedance by connecting to the sheath and possibly putting an electrode on, rather than fixing a network fault, because obviously, as you can imagine, networks, cables in the ground cost a lot of money to fix and repair. So just on to one of the last bits, RCD performance. RCDs are a wonderful bit of tech. They've been out for many, many, many years, since 1939. Some of the examples where we had voltage, fault leakage breakers, VOE LCBs, RCDs to BS4293, BSEN 61008, and BSEN 61009. So we've gone on a huge journey of making the earth leakage protective device accessible to the market. And all it's ever done is improve safety. You know, it protects against fire and it protects against, indirect shock. So it's a good thing if it works. And Krish's excellent webinar kind of raised a few points on the correct selection, erection, and configuration of RCDs, because some of these do rely on a functional earth connection. Now, I wanted to give you a few little gems, little nuggets, really, to kind of bookend Krish's excellent webinar. The pictures kind of says it all. BSEN 5178 in 1998, it clearly showed that if you had something where DC pulsating current could occur, you would configure the installation in your board separately. So you've got type A RCDs protecting circuits, a time delayed RCD to ensure you have selectivity, but then separate to that, a type B, which give you more immunity to DC. And if there was leakage, it wouldn't saturate or blind the type A. So this is what I keep saying to people. Configuration is key. Configuration of your protective devices, configuration of your earthing is incredibly important. If we fast forward to 2021, it's actually 2022 that came out, and it's mainly a product standard. Electricians generally don't know about it, but I find this chart quite fascinating. So BSEN 62477 part 1, and it talks about power electronic conversion systems and compatibility with the RCD. Well, that's interesting. So it's plug connected and it's greater than 16 amp or 3-phase. Then we ask, does it cause a DC current? And if it does, we take cautions, and then potentially we apply type B RCD. And if that won't work, we then apply another protective measure. But if we have plug connected and it's less than 16 amp, then we're recommending a type A compatibility. But yet in our wiring regulations, we still have type AC, although it's strongly recommended that they're not used, and they have been banned around various parts of Europe. So it's really important that you look at, what will my fixed installation do? Is it a communications rack? You know, will it produce DC leakage from the switch mode power supplies? Of course it will. And if it does, is type A enough? Have we done enough? One of the interesting pieces in this was when you apply another protective measure, one of the recommendations was double insulation. So double insulation plus your type B. So that way, if your RCD didn't work, you still have that the additional measure of double insulation. So there's some fascinating knowledge in the standards that help you consider your RCD protection more. We don't generally put one RCD covering everything. We used to years ago as main switches, but we kind of realized that there was a folly in doing that using voltage reference points. So now we've gone on a journey where we subdivided the installation, and we're now at a point where I'll show you an image where we have RCDs in each way, which gives the optimal subdivision of the installation, ensures earth leakage can't cause nuisance tripping, and if there is a fault, we minimize the impact to the user, which is what a good electrical engineer should be designing for. Now, for those who are on that learning journey, I certainly was, and still am. Fuses, fundamental principle of protection there. Current flows under fault, the element gets hot and it blows. That's your fuse. Your MCB has two components. That's BSEN 60898, or formerly BS 3871. And that has a bimetallic strip which can get hot, or a little electromagnetic coil which will look for an imbalance. And there are millions of MCBs around the UK. We've obviously been on a journey, BS 4293, standard RCDs, which we would use to put two of them in a board and split the installation in half, and that would look for earth leakage up to 30 milliamps. Thankfully, we have technology, and the wonders of technology allowed compact RCBOs, which you then have a little neutral reference lead for, and that's kind of standard what we do now in most installations, probably in the last 5 to 10 years in the UK. And that's a type A as well. Now, interestingly enough, some of them have additional leads as well, functional earths, because some of them may rely on a connection to earth so that they can operate and function correctly, get an earth reference. But when we're on that journey of selection and erection, or selection of our protective devices, we're now in a world in England where we have an arc fault detection device to BSEN 62606. We have surge protection to protect against atmospheric strikes and strokes. So strikes being a direct strike, stroke being the after effect, where you could get transients of thousands of volts. And we then do staged protection to ensure that any voltage spike within the installation, it dissipates and is protected and connected to earth. So there's a device that's essential to earth. We now have the OPDD, which is soon to have a standard. And that's the open pen detection device. And there's one that's been manufactured by a British company called Mate, and that looks for a supply neutral loss. So it's a device that effectively can protect against hazardous rises in voltages. So that's something that's fairly new in the UK, and they have a whole suite of devices that can protect. And if you look around the world, you've also got something called a POP device. Now, a POP device, similar to a surge, but rather than looking for thousands of volts, it will look for voltages outside the normal bands. Say you go and you get 290 volts single phase to earth. It will look at that for a few seconds and then disconnect to protect your installation from any stresses or strains because of the network. So there's lots and lots of devices now we have to pick, and we have to configure them correctly as well as our earthing. Now, there's two types of RCDs I just wanted to skip through. Voltage independent, must comply with the International Standard 61008, parts 1, 2, and 1. And these RCDs rely on the energy of residual current to activate the RCD. So the leakage current, that residual current, that's what activates it. They are often referred to as the old clunky electrical mechanical RCDs, and they are voltage independent in operation. Okay, so we then have voltage dependent, and they require compliance with 61009, 1, 2, and 1. And these RCDs use the mains voltage to power an electronic circuit and the tripping mechanism to activate the RCD. So they're referred to as electronic RCDs and are voltage dependent. Now, the majority of RCDs out there are electronic ones. They're voltage dependent. The older ones, it's always been said, will work if you have a loss of neutral, because it's obviously, if you lose the mains and you still have some energy there and there's a fault, you can still operate that device potentially. What are the advantages of voltage independent? Well, loss of neutral. The loss of this is directly from a white paper. The loss of neutral may happen for 7 reasons, and anywhere, unless we're in a TNC, which we don't recommend. Both in multi-phase and phase to neutral supply lines, the cases of unwanted interruptions to the neutral conductor can be defective breakers that do not close the neutral, loose connections, works on electrical lines or nearby electrical conductors. In the case of a loss of neutral, hazardous voltage is still present, but the voltage dependent RCDs cannot trip in case of this fault. with risk for human life. It is commonly said that probability of loss of the neutral is negligible, but as you can see, it is growing. So we need to just be mindful of it. Power against overvoltage protection devices could be an answer. OPEN devices could be an answer. In the UK, people are exploring that and very successfully exploring it. So it's still an exciting journey we're on as to how we select and erect best. But one bit of advice, please check in your standards for the special national conditions in the appendix. So this is BSEN 61009. That's a combined MCB, RCD with overcurrent protection. And it has some little overcurrent special conditions that say in Ireland, 61009s, depending on line voltage, can be used. You can use unswitched neutrals. In the UK, where neutrals reliable at earth potential, RCBOs with unswitched neutral are permitted. But what if you don't have that? What if you have an installation where you have single pole devices and you have diverted neutrals and a rise in neutral current? Then surely you don't have a reliable earth potential there potentially. So it's worthwhile looking through your standards to see if there is any national conditions. Now, this is my favorite picture of all time. It's my fuse board downstairs. And that is what I call a minimal viable product. It is a fuse box, a very witty pun from the manufacturer. It's actually a consumer unit. And what I have there is my installation. It's 21-way board. And I've labeled it all up. And each one of those devices, except for the surge, is an RCBO. So if there is a fault on the boiler controls, it only trips that. Sockets externally. So I have the added protection of an MCB and an RCD for every way. And I have surge protection. So that's a standard board. That's probably about £100 for the board plus the devices themselves. So you're looking at maybe £300 to £500 for a fuse board in England. But that gives you a very robust benchmark for safety. So that's my one downstairs. Kind of final thought, really, while I've been on this journey, and thank you very much for coming on it with me. Indian Standard 732 and SP30, it is not permitted to use voltage-independent RCDs in domestic and similar installations. However, in my opinion, and I'm sure Krish will agree, the prohibition in the Indian regulations may not be the right approach. Maybe there's a little bit more work needs to be done there. We also need to think, what devices in relation to earthing do we need, and how many do we need to select? We need to check our standards. Configuration is key. We need to keep up to date. We need to go on that journey. It doesn't matter where we are, as long as we're on the journey generally never ends. And most importantly, to everybody out there, stay safe. Thank you very much. It's been a roller coaster, and we'll go to the questions. Please watch this back on YouTube if there's any more bits you want to message me on social media and say you're wrong, or I've had another thought. But thank you. Over to you, Gopa.
Thank you very much, Mr. Paul. This was a fantastic journey, and as you said, the roller coaster. But anyway, we will be uploading the video in our YouTube channel, so those who wanted to look into it, they can look into the video, and they can also post their comments in the YouTube, so that we can reply to them on a later stage. We have few questions, approximately 15 questions are there. I would like to take up these questions. Also, I agree to you, Mr. Paul. You told that the voltage-dependent RCDs are not allowed in India. I don't know from where this started, but probably in future we will also we will start asking the question why this is not allowed.
I think I know where from, because the electromechanical devices are very clunky and old and expensive, whereas electronics are cheaper. So a lot of the manufacturers are not making them anymore. And that's where it's come from. From my research, that is. Please feel free, if you're a manufacturer, to tell us in the comments. Excuse me.
I could see that in one of the old versions of 7430, somewhere it was written that voltage not the new one, the old one, voltage operated RCDs are. Some comments were there. I think probably it also started from that particular point. So you also showed the SP, the CP1013. I have my copy here. The CP, I bought it 20 years back. The old British standard code of practice, CP1013, 1965. The Indian standard code of practice of earthing, the first edition was published in 1965, 66 in fact. Also, we had the IS 732, which was published in 1958. So we also have actually maybe a long history. So first of all, let us go through some of the questions. The first question is from Mr. Sanjay Mulai, whether supplementary equipotential bonding will help to clear fault. Is the first.
So there's a yes and no in that. It will help to equalize potentials. So it will give you equipotentials between two conductive or extraneous parts, not necessarily help clear the fault unless that link creates a lower impedance. We used to in bathrooms, which is a high risk in houses, cross bond, supplementary bond, everything, the lights, the radiators, the taps and everything to try and ensure where there was a high risk in bathrooms that we would ensure that there was equal voltages. But I mean, it depends on the installation. If you've got a large industrial installation and you're putting supplementary bonding in everywhere, then possibly. But in England, we don't kind of do that much supplementary bonding anymore. It's kind of only where it's required via either test or it's a special location that requires it. We used to bond everything. Everything got bonded. In the 15th edition, we bonded metal window frames, doors, anything that was metal got bonded. It was insane. You had pigtails and coils, and we went a bit mental, to be honest with you, doing that. But I would argue that not really, unless the connection of supplementary bonding leads to a lower impedance, then that would form part of the protective measure. But that's not really what supplementary bonding is about. Krish, I've done loads of talking. You can give your opinion now. Need to drink.
No, I agree. Sorry.
No, yes, Krish.
No, so I think that it's just to create it's just to reinforce the equipotential zone and make sure we're staying within that 50-volt touch limit. Like Paul said, it's only if it creates an even more low impedance path. But generally, that I see that happening. So yeah, the point is the equipotential bonding creates the the equipotential zone, and it has to go back to the source, which is the transformer, and that's what the protective earthing is for. So yeah.
Yeah, actually, the supplementary equipotential bonding is its main purpose is to reduce the touch voltage. So it's not for taking the fault current. That is what is defined so far in these standards. So, Mr. Paul, we have another question again from Mr. Sanjay. Generally, in a healthy earthing system, how much leak maximum allowed in the earth conductor?
Sorry, say that again.
What is the maximum allowed earth current, continuous current through the earthing conductors or through the protective conductors?
Right, leakage. Okay, yeah. So, hang on, my computer's going weird on me. Apologies. What is happening on my computer?
Actually, in India, this is a big issue because most of the time we have the habit of using non-standard products. As a result, the leakage currents are much more. Also, sometime I was coming across this situation, especially variable frequency drives and places where semiconductors are used. The leakage currents are much more, sometime in 200, 300 milliamps and sometime even in amperes. And we also have a funny device sold in the market called as a digital grounding device. These guys, it's a black box, and these guys make a short circuit between neutral and earth inside the installation or closer to a machine. Over to you, Mr. Paul.
Okay. So generally what we have is a rule of thumb in the UK. So we have a percentage of the circuit. So with a 30 milliamp RCD, general rule of thumb is no more than 10 milliamps, really. There is actually IEC papers on the correct usage. So IEC Technical Report 62305 gives guidance on how to work out leakages. So part of that selection and erection of a circuit, there is actually a formula where if you can go on, say, Schneider, Google Schneider, they'll give you a breakdown of all of the product leakage devices, product leakages, so kettles, cookers, showers. And what you can do is, let's say you have a PC or a laptop, you may have 2 milliamps. So when you're designing that circuit, you want to design the circuit so the leakage doesn't go above your 30 milliamp threshold. And obviously you want that tolerance of, switching on surges, etc. So you generally design it for, say, about 10 milliamps. And what you then do is you go, how many products can I actually connect to it? So if you take the 2 milliamp rule, you can then go, 2, 4, 6, 8, 10. So you've got 5 devices. If you apply a 0.75 Factor to it, you find that you can probably put 6 or 7 devices in a healthy RCD protected circuit. But again, as a designer of the installation, at the moment in the UK, there is only a requirement to be mindful of the earth leakage, not overwhelming and tripping the device, henceforth subdivision of the installation. There's no real fixed rule other than a percentage of the circuit, which is about 10%, if I remember rightly. Krish, you probably have got it in your brain off the top of your head, but it's early for me.
Even in the IS 732, it is there. Even for a fixed equipment, more than 20 amps, the maximum leakage current is 10 milliampere. But if devices which is using semiconductor or Y capacitors as filter, then the leakage current will be more. But there are measures to handle it. These are also explained very well in IS 732.
And we need to be mindful as well that all electronics now, in their natural performance, will leak to earth.
Yes.
So you will get natural leakage. So if you put a clamp meter on an earthing system, you will get natural leakage, and that can be perfectly healthy. It's when you try and disconnect an earth wire and it blows up in your face, that's when you need to be mindful that there could be a problem. Okay. Henceforth, configuration is very important.
Yes, very, very important. So the next question from Mr. Vivek Tiwari. What is instrumentation sensitive earthing? In Indian context, the European OEMs connect all earthing. Okay, basically, I will explain you, not going through the question. For example, most of the machines, let's say, for example, the biomedical equipment, the European system, the European machine manufacturer in their catalogs, they very clearly explain how to make equipotential bonding. But the same supplier, once when it comes to India, they ask for a separate connection to a separate earth electrode, and they call this as clean earthing. This is a big problem which we are facing in all over India. What's your opinion about this?
Oh dear, the good old-fashioned clean earth, eh? Oh blimey. Yes, clean earth. I remember hearing about clean earthing 25 years ago, and I was like, okay, how is it clean? Do we wash it? What do we actually do? How do you clean this earth? Now, if you think about that video I showed where you've got that energy dissipating, now imagine in that IT center, I have a rod and I call it my clean earth. How's it clean? Energy dissipates through the ground. It gets picked up on all conductive systems. Unless you put some sort of diode system or some weird over-the-top engineered system, you're not really going to have a clean earth. I do know of one place where they did put a one-way diode on an earth to stop it coming into the installation, and they call that a clean earth. But I don't believe there is such a thing as a clean earth. Happy to be told otherwise by my peers, of course.
Yeah. Actually, what happened is some of the equipment manufacturers, the Indian manuals, they modify it and they remove the equipotential bonding part and they put this separate earth electrode, because everywhere people have the impression that the symbol 5019, that the earthing symbol, they think that it is a separate connection to an electrode in soil.
No, that can be for a CPC, a circuit protecting conductor. I don't think I would put an earth electrode for every single piece of equipment. I couldn't guarantee the safety or the performance of the equipment. One thing I will say, if you don't mind me, is manufacturers, bless them, they will tell you anything they can to sell you stuff. And that's not a besmirch on all manufacturers, but I have heard some whopping lies from manufacturers to get me to buy stuff. Good engineers trust but verify. And we do need to understand, yes, that little symbol for earth doesn't mean electrode. It just means connection to the earthing system, a correctly configured system. And what you want is one point. Let's put it like this. If you had a building where you had a supply earth and then a local earth at a piece of equipment, and you had energy dissipating underneath through the ground, you could pick up energy into your equipment and then back through the electrical system. So you're actually allowing energy to flow through. So you're effectively allowing diverted fault energy, which is referenced in IS 732 and SP 30. It talks about diverted fault energy. So this is why configuration, I am a big fan of one point of connection to the general mass of Earth. If you have more, make sure it's configured and controlled correctly.
Yeah, actually, the wrong ideas came into the picture, or because of some of the misinterpretations of the earlier regulation. But in the current regulation, which was published during June 2023, it has very clearly written that earthing, the definition of earthing has been changed, and earthing means equipotential bonding. And every building shall have equipotential bonding. All these are now very clearly made, and probably we can see the changes very soon. So thank you very much for that answer. Now we have a question from Mr. Ullas Vajre. When we talk about equipotential bonding, even connecting gas and water pipe as shown in the figure shown by Mr. Paul Meenan, however, IS 1646 clause 8.2 state that in no case shall gas, steam, sprinkler or humidifier pipes be used for an earth connection. So is it not a violation of this clause?
That's a really good point. So I am going to default to your expertise there, but in England we have commonly always bonded gas and water, and interestingly enough, the reason we have always bonded gas and water is many years ago when the supply networks first started, it was imperative that the gas and water pipe was used as part of the earthing system. However, obviously that energy flowing and increased energy flowing has corroded and been detrimental to the networks. So in England, a lot of the networks are now converting to plastic polypipes, which then unmasks hidden problems. So houses where they may have a failed earth could have been masked via a lead water main or a gas main. So I'm actually kind of pleased to see in your regulations it says no gas, steam or sprinkler, because let's be perfectly frank, if you've got current flowing through your gas pipe and there's a leak one day and you get a spark, you've got an explosion. So hey, it's an interesting one. Maybe it's we have to ensure that all our supplies have got insulated inserts, non-conductive, and then maybe we do some supplementary bonding to protect further. But that's a really good point. Good, yeah. Let's update our regs. That sounds like an advancement.
There may be chances for mistakes also in this standard. This whole standard, for example, if we look at the IE rule or the CEA regulation 2010. Regulation number 41, sub-regulation number 10, what it writes is, no person shall make a connection with earth by the aid of, nor shall he keep in contact with any water mains not belonging to him, except with the consent of the owner thereof and the electrical inspector. So the regulation says, if without permission from the owner of the pipe, you are not supposed to bond. The regulation never says that you shouldn't bond. That is not there. But in a way, you get the permission from the owner of the metal pipe and you bond it. That is what is written. But what happened is this was misinterpreted, and people start reading only the first line. No person shall make connection with the earth. So only that part, if you read the first line, if you read it, gives an impression that you should not connect.
I think the gas one is valid. Steam, sprinkler, stuff like that, yeah, we would probably still buy. Again, if they're extraneous, we test for if they're extraneous, because you're trying to mitigate the bringing in of hazardous voltages to ensure that you don't get a shock when you're making a cup of tea and leaning up against a radiator or a steel structure. So, but the gas one, I kind of do agree. I think gas, possibly, maybe we need to do something with the pipes to take that out of the realms of bonding those pipes. It's an interesting one for debate, Krish.
I just wanted to add something. So the standard Mr. Vajari is referring to, I think it's referring to the fact that you shouldn't use a gas pipe, a steam pipe, a sprinkler pipe, or a humidifier as a means of earthing. So that's as an electrode. That obviously you're not supposed to do without in any case. So that's similar to what 7671 says as well. You're not supposed to use those as an electrode.
Yes, no, you shouldn't be. No, although we do by default.
Equipotential bonding anyway.
Yeah.
So in simple conclusion, you must bond it, but you should not make it think that the whole fault current is, or don't allow the fault current to flow through this route. That is what is necessary. So the next question from Mr. Sanjay Mulai: in case of TNCS system, if the neutral broken, then what is the protection to avoid overvoltage in distribution system?
So as I said, at the moment, the go-to thing in England is these OPDD devices, open pen, protective earth neutral detection devices, seem to be the great next hope mitigate that. The bigger debate there is the lack of product standards at the moment for it, the risk of introducing any new technology, its performance, obviously. And also there's a bigger question of why are we mitigating for the supplier's failure? You know, why does the homeowner have to pay because the electricity network that you pay your money to in your bill hasn't to maintain the network? But again, I suppose it's your risk appetite. How much are you willing to pay to protect your home, your family? Do you have correctly configured bonding? Do you need it? Do you want it? You know, do you want to have a power over voltage protection device? We don't have them in England at the moment. They're in Europe. But the OPDD devices, the open pen detection devices, they do look promising. I'm still looking into them in greater detail. But I think for me, you can't beat good old-fashioned earthing and bonding as your fundamental measure for protection. Look at that. APOP Eaton. Krish has got his stuff.
Okay.
Oh, yeah, that's a big one.
But in India, we have some kind of over voltage relay, so which measures the voltage and which try to trip, but unfortunately it measures the potential between neutral and the live conductors, phase conductors. It's not a perfect solution, but sometimes it is a solution.
The MAT-A stuff effectively measures between phases or phase and neutral and creates like a ghost Earth reference that it can reference against the real Earth. It's quite clever electronics. I'm still looking into it, but it does look and appear to be a viable solution, and it seems to be used a lot in electric vehicle charging technology as well.
Yeah. So thanks for the answer. The next question is it recommended to install RCD as a mitigation if fault loop impedance the test fails? That means as a measure for fault protection.
Yes, it is. However, there is a folly of our industry. So we got it wrong. We have this rule. That's a very terrible rule of the 1,667 ohms. You can allow 1,667 ohms if you have an RCD, but that's great. But that still doesn't offer you any protection against fault currents. It's only earth leakage. So if you have 1,500 ohms, yes, if you have earth leakage, you can rely on your RCD. But if you have an overcurrent, you've got nothing still.
Yeah.
But good earthing, good low impedance will allow sufficient energy flow, and Krish is going to carry on.
I just like to add that about falling back on the RCD. If you look at clause 4.2.11.4.4 in 732, it also does mention that where compliance with this subclause is provided by an RCD, so on and so forth. The point is that you're only supposed to actually rely on the RCD for fault protection if it's not achievable, if the loop impedances are not achievable. So just because the cables are undersized, it's not an excuse to say that, okay, we're not achieving fault protection through our OCPD and ADS, and then we fall back to the RCD. You want to achieve fault protection through automatic disconnection of supply, which is equipotential bonding, protective earthing, and automatic disconnection of supply. You want to do that ideally through an OCPD. You only want to fall back to an RCD if and only if it's unachievable. Not that if there's a non-compliance and you just bang in an RCD and then achieve compliance.
Yeah, we did some bad things by creating that horrific rule of thumb, because it became a rumor or a wives' tale in England where 1,667 fine. They test, they do it, they wouldn't think, and that we should always think. We should always be thinking.
Yeah, the next question is again from Mr. Sanjay Mulai. Is IEC 60364 and BS 7671 both are similar, or is there any difference? The earthing part.
7671 basically takes its guidance from 60364. There'll obviously be local conditions that are agreed by the JPEL committee, but fundamentally very much we're very aligned, to be perfectly frank. Any real local UK conditions, we have a 200 number against them. But yeah, we're very aligned, basically. We just use our terminology, but no, 60364 part 5, part 54 is our chapter 54. So we are very aligned. Who knows how long we will be aligned for, because it's ever emerging and ever changing. But yeah. Also, just on that last one, RCDs, by the way, it can be used it has to be used for a TT installation where you only have an electrode. So that's for fire safety, obviously.
In our standard in IS 3043, what we have written is if the fault loop impedance is failing, that means if your OCPD is unable to disconnect in case of a fault, then you should put an RCD, and the RCD I delta N is 30 milliampere. Probably 30 milliampere may not be required for fault protection, but this is what is written in the standard, which has originated few years back. Anyway, the revision of these standards are still going on. We will seriously look into it. Actually, we have an interesting question. The next question from Mr. Lokesh Ashok. How to figure out between TN-TT, TNCS system? I think the same discussion we can even have after 50 years, probably in India, because this is the most confusing subject. Majority of because the electrical safety is not a part of our curriculum in the engineering. It's not a part of the subject, engineering subject. As a result, the confusion of this system earthing is very much prevailing in the market. People doesn't know how to how to make it. So if you don't know how to make it, then how to check it is the next part. If you don't know to make it, then then you cannot check it. Basically, the DISCOM engineers, the distribution company engineers, maybe 90% doesn't know this subject. I am sorry, the participants, those who are listening to me, it's a fact. You should accept the fact.
It's an interesting one because we were taught when I was in college that it's very easy to look at supply intake and understand the earthing configuration. But over the years that I've been on my journey, the networks have failed and they have hybrid. What was a TNS system, very clearly separate neutral earth on the sheath. But when you go into the substation or into the cable behind the house, you'll find that the neutral earth are linked. So what I've found over the years is what I think to be a TNS. And I wrote to my network and said, is it reasonable to assume that the TNS supplies in my area are actually TNCS or PME in the street? And they actually wrote back and said, yes, unless it's off a private transformer, private TNS, it's a very reasonable assumption because to keep the network running, the engineers will reconfigure it. And if you lose a cable, then they'll piggyback on sheathing and all sorts to keep that neutral earth connection going. So what you've got was what I call a Frankenstein network that's old, where everything that's earth is combined neutral and earth, which is not great for network balance. Because you've got so many neutral references, the energy dissipates everywhere before it gets back to the substation. So we've kind of created one mess to solve another mess. But yeah, I mean, it's by inquiry. I think is also in our certification, isn't it? By inquiry, obviously visual inspection. But again, speak to your local supplier is my recommendation as to how it all works.
Actually, we tried speaking to the local supplier, but local DISCOM. We call the energy supplier as DISCOM, distribution company. But fortunately, you don't get any answer.
Funnily enough, the DNOs sometimes don't want to talk to us either. Electricians can be very annoying to the electricity supply company, trying to do a good job, highlighting how bad their network is. You don't become popular.
Yeah. See, one of the problems which we face all over India is whenever there is a fault on the HT side of the transformer, mostly the system, low voltage system is TT, and whenever there is a fault on the HT side of the transformer, the low voltage side, the connected equipments are failing. And it's in my view, the DISCOM has to be penalized because we are paying for electricity and we are taking their troubles into our house and our equipment are burning. Unfortunately, legal system has to be improved, and I'm sure it will happen soon.
Yes, totally agree. I think the same in England, that the electricity companies should be held with their feet to the fire far more clearly by the governments, without a doubt.
Yeah. So we have a question from an anonymous attendee. If the power supply distribution, actually once when they log in, some people don't want to put their name. So they feel that, making their name public maybe is dangerous.
Hello, anonymous.
Yeah, anonymous attendee. If the power supply distribution company does not confirm the type of power supply network provided, is there a method available to identify? I think this is the same question which we had earlier. Further, how can one differentiate between TNS and TNCS network on the site? Because I would like to skip this question. Gentlemen.
Visual inspection is the answer to that. That will tell you straight away is what is the means of connection between the earthing and the neutral of the electrical installation. So does the earthing connect to the sheath of the conductor? You could ascertain it's separate. Does it go into the fuse cutouts or the fuse heads? You can ascertain that it's a combined neutral and earth system. But again, it's kind of a joke. So I did a webinar on my E5 page where all we did was coding of intakes, and it was taking people on a journey of the older stuff, sharing our knowledge of that's a service intake, it's a TNS, it's a TNCS, what are the hazards? So we did a long webinar on that. If anybody wants to watch it, please go ahead. It's quite enjoyable looking at some of the hazards in England and the different cutouts. At the end of the day, this is the knowledge that we're not very good as an industry at sharing. So henceforth, we did the webinar on it. But I'm sure you guys have got pictures of intakes which would leave me guessing as to whether it's a TNS, TNCS, or some weird Frankenstein butchered version.
Yeah. Thank you. There is a question from Mr. Chesring Hosfell. It's not an Indian name. Sorry to pronounce bad if it is. Is it advisable to connect a earth cable to reinforcement bar of the building, as it will eventually lead to corrosion of the steel bar in long run, posting a threat to structural part of the building?
Really good question. What is the term? It's on the tip of my tongue. So there is potential, yes, if you connect an earthing system to steel reinforcement, that you could actually get, we called it concrete cancer. Oh, it's especially fraught on DC railways where you have DC traction. So the basically the DC will absolutely eat the especially on railways. If you bond, say, an overhead line system to a car park, that car park steelwork will just degrade at an accelerated pace, whether it's AC or DC. So for the bigger systems, yes. For a domestic small house, I would suggest no. But then again, on larger buildings, you bond the structural steel, so you are creating a path anyway. For Crossrail, we used a pile cap wall that was designed for like 175-year life, and it was just purely HV for the tunnel boring machines and stuff. So short-term use. Again, it's kind of understanding when you're giving the supply, what is it being used for? What are the hazards that are going to be provided there? Are we connected to a DC traction railway? Is a perfect example, because that will corrode everything and anything near it structurally. Is that an acceptable risk? Again, these are all things that need to be asked in the design phase. But it's a very, very good question. And I'm annoyed now that I can't remember the phrase. There is a phrase for this effect, and I have a white paper on it. And there are white papers online that are fascinating that show car parks that have almost collapsed. And I can't remember it, so apologies.
Yeah. So basically, for in case of AC, there is absolutely no issue. But the connection for large buildings, anyway, the DC current flows are there. If you are near to a DC traction system, some of the cities in India have got DC metro railways.
We could do a webinar just on that. That's a webinar in itself, just that. The effects of AC and DC on structures.
Okay, that would be great. Thank you. Thank you. So again, from Mr. Chosfal, do we have regulations in India to follow which type of earthing system, TT, TNS, TNCS in a distribution network? Mr. Chosfal, this is a very difficult question. There are regulations, but the problem is only few people read the regulation, and the majority of the people doesn't know or the DISCOMs doesn't doesn't want to follow any of these regulations, because they have the systems which they were following for decades, and they feel that it is the best system they do in paper. Most of if we look at in the DISCOM, 99% cases, instead of compliance, we can see non-compliance. So this is the main reason for death of almost 14,000 people every year due to electrocution in India, one of the largest maybe worldwide. Majority, about 50% of these accidents are happening in the distribution. Also, about 50% happens within the consumer premise, because most of the time, if there is a fault in the consumer premise, the incoming fuse is not blowing because there is no earth fault protection, for example. So there are several reasons. It's a big, it's a Pandora box. If we open, we can discuss for several days. So there is a question from Mr. David. Is there a test that can be conducted to determine if a metallic part is of extraneous potential?
Mr. Betteridge, hello. I'm going to allow Krish to answer this one. He knows. Yes, he knows there is. Go on, Krish.
Yes. So, well, you've got to basically test the resistance, and there's an equation. I know it's in guidance note. Which one is it? The one for earthing and bonding. And if it's between a certain value, this on top of my head, then it is extraneous. If it's not, then it's not. That's right, right?
Yeah.
Just open the guidance note up. Hold on.
Oh,
So just on that term I was looking for, cathodic protection is a whole bag of how we use energy to counteract corrosion we could talk for hours on this.
so the question from Mr. Vivek Tiwari: what is the significance of neutral to earth voltage? What is the safe value? Many OEMs, especially Europeans, ask for this value to be less than 1 ohm. Mr. Vivek Tiwari, it is not the European OEMs those who are asking this voltage. It is the Indian counterparts of those OEMs asking this question. But however, to Mr. Paul.
So this is an interesting one because the network providers now, when they are analyzing their network, they actually do a neutral to earth loop impedance test. Now, if you're able to do a neutral and earth loop impedance test, you've got a big problem. You've got a big problem because that test shouldn't, in theory, be possible. But on a damaged network, a failed network, you can get a neutral and earth loop impedance. And I've seen people go across neutral and earth on a system where it's been so poorly connected and it's just basically corroded in the street, where you actually can get voltages between the neutral and earth, which is quite scary, especially when you're around railways and stuff, because if you get that, you can end up blowing up equipment quite easily. But yeah, generally as low as possible. In fact, zero really, because they should be one and the same. But yeah, you can test it. You can test it in your boards. See if you've got continuity between it, stuff like that. Yeah, you'd have a big problem if you had more than a volt or more than a few volts between neutral and earth.
Yeah, I actually have a different view here because now
go for it.
New standards, the functional earthing need a zero reference potential, and now the standards are saying the functional earthing has to be separate from the potential, the protective earth. So as a result, the if you look at the ISO 30129, more information can be found. But here the Indian context, the problem is everybody wanted to have less than 1 volt between neutral and the earth. Then my question is, if you have a IT system between the distributed neutral and the earth, probably the voltage is 150. Still the system works. And the system has to work, especially in hospitals, for example. So this 1 volt is technically, if we look, it is not actually applicable. There are methods probably derived to handle this question. Probably, I think we can have a webinar alone on this subject.
Oh yeah, we could probably do 10 from these.
Yeah. I'd just like to so the question that Dave asked, is there a test to identify if it's extraneous or not? The value, the equation I was talking about was, does it need supplementary equipotential bonding? So Paul, do you have an answer for the question that Dave asked?
It's the 22,000 ohm test, basically your wander lead. So you effectively go from the main earth terminal and you go across all of your exposed and conductive parts and basically measure less than, well, if it's not 0.05, you can go between items, and if it's over or above 22,000 ohm, you can decide whether you do bond it or not bond it. It's in guidance note 8. I believe it's only a 10 milliamp current. Years ago, we used to put like 20 amps through the earthing systems and see if you could see sparking and arcing from loose connections. But yeah, there's lots of ways of doing it. There's obviously your 0.05 value, or there's your defining whether it's extraneous and your 22K test. I think there is a paper out there somewhere on it. I'm sure we'll probably dig it out and do something with it.
So it's just basically the whole human body resistance thing.
Yes, in proportion to it. Yeah, effectively.
Got it. Okay. Thanks.
Thank you, Mr. Paul. We have a question from Mr. Pavitran. For lightning arrestor, individual earth pit installed, but if it is connected to the other earth plate of the building, is that dangerous?
I will. So by default, it can be. So depending on your lightning protection risk assessment and the system that you use, I mean, a lot of places now use like the rolling sphere method, but you can have a connection from the lightning protection strap to your low voltage terminal. I wouldn't necessarily connect both the LV earthing conductor to the same pit for an electrode, but I would run a bonding conductor to the earthing terminal from one of the straps to ensure that rise and fall in potential is the same. You can get obviously transient surge protection. So if you go to a lightning protection company, they'll recommend say 8 rods around a building, copper down conductors, and a surge protection type 1 surge protection device on the mains, so that if anything does enter, it can dissipate it accordingly. But again, that's a 62305 is another specialism. Lightning protection is a specialism in itself, one that we need to be at least aware of. And if you want more information, go online and Dane do a red book, which you can download for free, and it has all of the 62305 stuff in plain English.
I'm taking classes for the last 25 years or 26 years on this subject all over India. Maybe if I count, probably more than 1,000 classes I have taken. Still, the problem is, first of all, the question, say, for example, lightning arrestor. What do you mean? Do you mean in a distribution surge arrestor or a lightning air termination system in a building? This is the first question to be asked back, because in the standards regulation, it is also, people try to, the regulation says, there is a mistake in the regulation, number 74. It says, the lightning arrestor in the distribution system, it has to be connected to a separate earth electrode and then to the grid, to the plate. This subject is very, complicated. But Mr. Pavitran, as an answer, of course, you must bond. You must bond with the shortest wire length. So, yeah, you can also, We also have published a lot of these books. We can send you these books. Please have a look on it. But your question should be clear. You are talking about a building or you are talking about the public distribution system. So coming back to the next question, Mr. Vignesh M, IEC 62368 clause 5.6.6.2, it says AC or DC and the test voltage shall not exceed 12 volt. Which will be more stringent, AC or DC, and why they have considered? Actually, I'm sure you are able to see the question, why they have considered 12 volt, why not 30 volt? I'm not aware of this particular standard.
6.2, I think that's mainly because a lot of the outputs of those switch mode power supplies is 12 volts. But again, I'm sure, let me see, 162354, hang on a second. See if I've got that in my wonderful collection. 62354.
It's for AV and information technology equipment.
Yeah, well, most of the switch mode power supplies 12 volt output, aren't they? But again, it's more a question for the manufacturers. You may find that they do. It depends on the make of the product. But I'm not familiar with 62368 anyway, so it's a question I couldn't really competently answer. I can give a view. 12 volts seems to be the output of most switch mode power supplies, but
yeah, actually, we have to understand what exactly is the subject. In a webinar, if you ask this question, we have to refer, and it takes a lot of time to refer and answer. So probably
another webinar in that as well.
We can maybe he can write to us, and we can answer on a later date. So there is a question from Mr. Amritlal. The public network of residential small commercial installation, the supply is by TNS or TNC in UK. For new network.
Well, TNC generally is frowned upon. TNC actually refers to the supply distribution anyway. So when you have a TNCS, it's separate within the installation because it's really quite, there's a bit of double standards with this. So TNC is not permitted within a fixed installation, but then the regs also say you can use it, but you have to meet a whole load of other criteria because it's deemed quite dangerous within an installation. It's always worth separating the neutral and earth. Generally, all the systems, all the wiring in buildings is always TNS. It's effectively neutral and earth separated throughout the fixed installation. In some buildings, in risers in the UK, high-rise buildings, they did operate a TNC system, so the neutral and earth are combined in the risers for tower blocks and then separated off. But generally, it's frowned upon. It's recognised it used to happen, but nowadays we try and keep it separate.
Okay. So probably we will take 2 more questions and close the webinar because we have, normally we try to make it to 1.5 hours because after 1.5 hours, really the participants start dropping. So probably after 2 questions, we will stop. The question, Mr. Bettridge, is can we test for touch voltage levels?
Yes, we can, and he knows we can. We can do it with our test equipment, and I'm going to challenge Mr. Bettridge to come on one of these webinars and discuss it with us. So most electronic test equipment, yes, you can actually use capacitors built into them to look and check for touch voltages. There are maths and formulas and books out there. But Mr. Bettridge, we will, I think we need to challenge him to come on and actually do a talk because he has my book on touch voltage testing.
Okay.
Which he didn't put in the chat, but I have a book on touch voltage testing and he's got it. So, Dave, you're coming on.
Yes, okay. Also,
podcast.
Few questions on lightning protection, Mr. Sajid as well as Mr. Kapil Dev Pandya. But for both of you, please look into our YouTube channel. We have NFE YouTube channel. We have made webinars on lightning protection exclusively, answering these questions which you are asking. For example, whether to connect the LVR thing and the surge SPD together and all these things. So both the questions we have answers. Please go through our webinar on lightning protection. I think we have 6 or 7 videos in our YouTube channel. You will get a lot of information. So probably with this, we can make a conclusion. Over to you, Mr. Paul.
So which question are we on again? There's another one that's just appeared up and it's distracted me.
All these questions are regarding lightning protection. We have videos which is already uploaded.
Yeah, I think with lightning protection, the one thing I've learned in my journey on lightning protection is configuration is key. One of the more interesting parts I learned is you're trying to arrest it before it gets in the building. And yet with a lot of lightning protection systems, that by bonding them, say on the roof, you end up introducing the faults into the building. So it really is quite I agree with you, Gopa. It's an incredibly in-depth discussion about the configuration and the risk to the building and what are you doing and how are you doing it. And I think it's fair to say that I've learned in my journey that a lot of lightning protection systems are fundamentally non-compliant. Everybody bonding everything together with tape and then wondering why stuff fails if there is a lightning strike. Yeah. It's about channeling that energy around the building, not through the building. But ensuring that people are safe. So, I'm going to have a look at some of your webinars now on that as well, because it's always good.
In our IEC committee, TC81, which is making the 62305 standard, I am a member in 6 working groups. If we look at what is discussed and what upcoming standards are, the upcoming standards are going to have a lot of changes and a lot of new information, in fact. Good. But whatever the webinars which we made and available in YouTube are from the existing standards. Of course, technology changes and always there is a scope for improvement.
Well, as I said earlier, that I've spoken to the chaps at Dane many a time and said, look, I really would like to see a 62305-5 for testing, inspection and testing of the system. So we've got a common product standard, but fingers crossed.
Yeah. No, we have a network group and we are working out on an inspection standard, or let's say 62305 part 3.1. Okay. So Yeah, it's on the initial days of discussion. Probably in next few years, these standards may come out. I don't know the current position situation. So with this, thanks to all participants, especially our sincere thanks to Mr. Paul Meenan to be present here. I think it is what is the time there now?
It is 8:25 in the morning.
Oh, okay. So you started early.
I was up at 5 a.m. and I was in bed at 2 a.m.
Thank you very much, Mr. Paul. You also told us to prepare this presentation.
It's been an honor. Thank you very much for everybody listening.
Yes, so thank you very much for giving this information to all of us. And fortunately, today is the World Standards Day. And we discussed a subject which is the history of earthing and bonding, the correct subject for the right day. So thank you very much, Mr. Paul. Thanks for Krish to be a part of all the NFE programs. Also, for all the participants. So we will answer to your question. The video of the program will be uploaded very soon, probably in another half an hour or 1 hour. You can find the video in our YouTube channel. So thank you very much. Thanks to all. See you.
Thank you very much. Cheerio.